New nuclear is on the horizon and can provide an effective zero-emission solution for heavy industry and transport, which are currently responsible for as much as 30% of all greenhouse gas emissions. To achieve this, nuclear needs to move from economies of scale to economies of numbers. Nuclear power is a true zero-emission technology, and it needs a mass market. Ocean transportation is a vital component of global trade, with over 85% of commodities, industrial components, and durable consumer goods transported at sea. Of the world's 100,000 ships, just 7,300 consume half of all marine fuels, and thus emit 50% of all greenhouse gases from ocean transportation. From 2050, the UN has mandated that ocean transport must be emissions-free. In 2018, Core Power was formed to bridge the gap and build the market for advanced nuclear technologies in the maritime industry. Today, Core Power partner with leading international companies to deliver durable, zero-emissions energy solutions for floating industrial production and deep-sea shipping, while also co-funding developments of advanced nuclear energy technologies which are appropriate for maritime use and lead the work to build commercial civilian nuclear solutions for shipping. Our industry engagement, regulatory consultation, design and engineering will result in a competitive, true zero-emission power system for the future of maritime from 2030. Core Power are actively participating in the work required to modernise regulations for maritime and nuclear, and to pave the way for small-scale nuclear to take its rightful place as a key pillar of global sustainability.
Hello everyone. Very happy new year to all of you, and although it's extremely cold in London this week, we'd like to extend a warm welcome to you all for Core Power Hour number 5, which is the latest in our series of virtual programs that have now been running since July of last year. This is one of our free to attend events, and with each of these online programs covering a separate topic on new nuclear for maritime, the idea being that this provides a taster as to part of the learning element of our client program. Now, for sake of good order, you may have heard at the start of the video there that this program is being recorded, and we'll be able to make a copy of the recording available afterwards. So if you would like one, or if you're aware of anyone that could not join that would like one, please just let us know. And in fact, the same goes for all of the previous 4 Core Power Hours as well. A small housekeeping point is that we would respectfully ask that you don't take any screen grabs from the presentations you'll see today. If there is a specific image that you'd like to see again, please contact us offline and we'll do our best to assist with that. I'm the Director of Business Development for Core Power, and I'll be your host and moderating the panel for today's session. Now, today's topic is focused on the commercial aspects of floating nuclear. And there are 2 or 3 key elements to this that we're going to introduce first in sort of a broader picture, and then separately look to delve into a few of those in a little more detail. For example, how mass manufacturing of a type-approved machine can radically change reactor economics for floating nuclear power plants. And then looking further ahead, some aspects of life cycle costs and residual values when it comes to future nuclear commercial ships. Now, following these short talks, there'll also be the opportunity to answer some questions. So if you have something that you'd like to ask or have clarified, please use the Q&A function there on the screens, and we'll do our best to get through some of these. It may be some we're able to provide a quick written answer to, and others we can take online and in person. Now, joining me, we have several panelists today. In no particular order, they are our Chief Executive, Mikhail Bowe, Tom Davis, who's on our analyst team, William Fenley, one of our marine engineers, and also joining the panel discussion later on will be Giulio Gennaro, our technical director. So welcome, gentlemen, to all of you. Now, William, it's your debut in the flesh, so to speak, on the Core Power Hour, although it's your dulcet tones that grace our introductory video segment. But thanks very much for stepping in to assist us today, and also for getting the ball rolling on this topic. The economics of new nuclear maritime need to be attractive. It's obviously one of the key pillars on which the concept is founded. And whilst it would be nice to think that there's an unlimited blank check available for the green transition, I think most of us will agree that operators of marine assets will only decarbonize if they can afford to. And by that I mean if the cost of green fuels is substantially more expensive than the existing options plus a greenhouse gas levy, then you can be sure that the latter route is sort of what the vast majority will opt for. So that's sort of a long-winded way, really, of saying whatever solution is proposed has to come with commercial benefits. So how can we be confident, really, that this will apply to new nuclear technology at sea when what we've seen from the existing scenario, i.e. naval reactors, is that whilst they do come with benefits, they also come with quite a significant host of challenges as well?
Yeah, it's a good question, Toby. And it's an interesting point about mirroring existing naval reactors into the commercial world. And although naval reactors have several benefits, they also have several challenges, challenges around operations, regulations, and liability. But hopefully over the next 10 minutes or so, I'll be able to explain why we think that new nuclear would be able to have the same benefits as naval reactors, but as well as mitigating the challenges, hopefully making it suitable for civilian use. Thank you. So I'll get started. Hello, everyone. I'm William Fennelly, and as Toby mentioned, I work in the marine engineering team at Core Power. As you know, we're building a market for new nuclear and maritime. The title of my presentation today is New Nuclear for Maritime, the environmental and economic disruptor. We have chosen this title in the hope that we can tempt you all to start thinking differently. To solve tomorrow's challenges, we must change the way we think of our energy use. These challenges are not just about the environment, but also about the economics of our industry. Shipping is the most fiercely competitive industry we know, and for a long time, we have been on a race towards zero emissions and zero margins. Nuclear has been beaten up since the 80s, with fear and mistrust fostered by those who would profit from its demise. These two industries are essential for a future of human prosperity, and both are ripe for disruptive change. New nuclear will have a very important role to play in tomorrow's maritime, and we believe maritime will have a very important role to play in tomorrow's nuclear. Here's why. The global push for a green energy transition and an environmentally sustainable ocean transportation sector will, at the end of the day, come down to the matters of energy density and energy efficiency. Simply put, the more fuel we use, the more waste we produce, and conversely, the less fuel we use, the less waste we produce. The waste varies, but it's still waste. And that's why energy content matters. Our current low sulfur IFO 380 contains an average of 41 megajoules per kilogram, which equates to just over 11 megawatt hours per ton of fuel consumed. Our industry's focus on synthetic fuels made from green hydrogen contains less than half the energy of bunker fuel, with green methanol containing 20 megajoules per kilogram and green ammonia slightly less. Our industry's transition to this end of the energy spectrum would therefore result in a more than 100% increase to our fuel consumption, with a corresponding increase in our waste from emissions, corresponding increase in our waste and emissions footprint. Nuclear fuel from uranium, which has been safely and efficiently used in power generation and nuclear navies since the 1950s, contains 80 million megajoules per kilogram, the equivalent of 22 million megawatt hours per ton of fuel. For easy comparison, that's roughly 4 million times more energy per ton of fuel than the proposed alternatives. Physics tells us that the quantity of fuel and the fuel efficiency determine the quantity of waste we produce. During the combustion of bunker fuel, carbon in the fuel reacts with the oxygen in the air, which creates approximately 3.2 tons of CO2 per ton of bunker fuel consumed. That's how our industry contributes 2.5% of the 50 billion tons of global CO2 emissions every year. LNG and green methanol would improve on this, whilst in green ammonia, the pilot fuel required would be the only source of CO2. With nuclear fuel, since we use so infinitely little of it, we produce negligible quantities of waste. This waste, while toxic and harmful if ingested, is never released into the environment, unlike exhaust gases. If it's not delivered or ingested, it's logically not harmful. If we are to produce a smaller quantity of waste and emissions, we must use a smaller quantity of fuel. Not less fuel by going slower, but less of a better fuel so we can go faster. Going faster on less fuel logically improves our economics. Since January 1954, there have been over 700 reactors built and operated around the world. About half of these have been operated at sea, and we know it works really well. So when our industry thinks of nuclear power, it thinks of naval reactors, but we must think differently. Naval reactors are not suited for commercial use. That's why we don't have nuclear-powered ships today. The benefits of naval reactors include millions of miles without refueling, true zero emissions, and because the reactor acts as an energy storage, we don't need fuel tanks, which gives us much more space for cargo. But the features of naval reactors makes it unsuitable for shipping. They are highly pressurized, which means we must maintain a large evacuation zone around them. This makes port calls all but impossible. Additionally, the fuel is highly enriched, which is a showstopper in civilian life. They are also tricky to operate and require a very high degree of active management by specialized crews. What we need is a way of getting the same benefits from a new set of features that are suited to our needs. New nuclear for maritime must be fit for purpose. Using unpressurized reactors means we can shrink the evacuation zone down to just the boundary of the ship. Operator liability would go from being a public liability to one covered by marine insurance. We can also use low-enriched fuels, which are acceptable for civilian use. In fast molten salt reactors, we can use those fuels so efficiently that we don't need to refuel for 30 years. The extreme fuel efficiency and a small quantity of fuel combine to produce very little waste. Importantly, we can, for the first time, manufacture these new reactors as a small mass-assembled product. Assembly line production means better construction and higher quality assurance. The emergency planning zone, EPZ, around a reactor matters, and is one of the primary reasons why nuclear as we know it today has not been adopted by the shipping industry. It is essentially the difference between unlimited liability of maintaining a large EPZ versus the limited liability of maintaining a small EPZ contained within the boundaries of the vessel. The examples you see here are illustrative of this point. In case of an accident with a large EPZ, the operator of the vessel would be responsible for the evacuation and cleanup of the area in the port and the whole port city. With a small contained EPZ, that liability would not extend beyond the railings of the ship and could be covered by marine insurance. It's a big difference. In waterways, as you can see on the right, where the EPZ is moving with the vessel, a large EPZ is an almost inconceivable liability burden for even the largest vessel operators. Again, a small EPZ, not beyond the boundary of the hull, changes all of that. Since we went from sail to steam in the 1860s, shipping alone has poured over 1 trillion tons of high-energy fossil fuels through our engines and released over 3 trillion tons of exhaust gases in the atmosphere. All that fuel had zero residual value. Not only that, it turns out pollution costs. Accounting for well-to-wake, fossil fuels have a negative residual value. What makes the fast MSR a real disruptor, however, is the positive residual value of the fuel. And here's how. Instead of stopping the reactors at refueling intervals to remove the spent fuel and load fresh fuel, the fast MSR, which runs on a liquid nuclear fuel, is topped up at full power. We don't stop, we don't produce any emissions, and the little residual waste, equivalent to that amount being topped up, we extract from the core and store securely inside the reactor island, with no harm to anyone. This means that the tank is always full. What went into the reactor on day one is still there, intact, on the last day. At 2.5% inflation, an asset doubles in value over 30 years. With a ship or a floating production platform for synthetic bunker fuels, with a lifetime of 30 years and powered by a fast MSR, the fuel in the reactor, all else being equal, could double in value. In the example shown, we have a $100 million asset based on a nuclear-powered Newcastle Max, a $150 million reactor, and a $250 million fuel inventory, with a total capex of $500 million. Consuming bunker fuel, the same ship with a $60 million capex, plus fuel at $600, and carbon taxes at $100 per ton, this would cost roughly the same, $500 million in combined capex and opex. Consuming green synthetic fuels like ammonia and methanol, we estimate the cost would quadruple. That's $2 billion, not $500 million. The economics of the same ship powered by a fast MSR has the residual value of the nuclear fuel going from $250 million on day one to $500 million at the end. As per industry practice, some value is set aside for a reactor decommissioning fund, OPEX, maintenance, and specialized insurance. The liquid nuclear fuel would then be drained from the reactor and loaded into the next generation fast MSR for reuse over another 30 years, and so on and so on. Financing the nuclear fuel becomes a very different proposition. We advocate for leasing. Very few, if any, commercial vessel operators would become licensed nuclear operators. With leasing of fuel, energy, and the reactor system, we can include the license, liability insurance, specialized reactor operators, and the maintenance of the system in the price. Here you can see the potential depreciation of the fuel for financing purposes and the actual potential value for the fuel under 2.5% inflation. It shows a lease margin, the spread between actual and financeable value, in which we can construct a viable leasing model at $300 million. That's 60% over the original capex. The EU taxonomy allows nuclear to be financed by green bonds. The US government is encouraging investment in new nuclear. Japan, India, China, Brazil, and Canada are all encouraging private investment into the nuclear fuel cycle. We want sustainability across the board, both environmentally and economically, and we think here it is. So I'd like you all to start the new year by thinking differently. Fear of nuclear is always born from a lack of knowledge. It's not that complex. A little knowledge goes a very long way to understand how new nuclear for maritime and maritime for new nuclear can provide the future we all want. To demonstrate the viability of new nuclear and maritime, we will need evidence of safety functions and systems so that we can always ensure safe and secure operations, even when a marine accident occurs. Now, nuclear is the safest energy source we have in the world today, despite widespread popular belief. Younger generations who are concerned with climate change and global warming are learning that nuclear is the safest way to convert energy to power, and that new nuclear technologies promise true zero emissions and a sustainable environmental footprint. With new nuclear, it's not about more safety, it's about how safety is achieved. We recognize that radiation, whether man-made or natural, is an essential part of our life on our planet. And like everything else, from red wine to hydrochloric acid, is nothing to be feared in suitable doses. Radiation is used to cure illness, not cause harm. Radiation limits set by international organizations are set so low, they are akin to having a motorway speed limit of just 1 mile per hour, as safe as possible or as safe as reasonable. Nuclear is the only reliable zero-emission energy source we have. The finest minds and the smartest people in the world are actively engaged in technology advancements that make this new generation of new nuclear machines fit for our purpose. And with that, I'll hand back to you, Toby.
Well, thanks, William, very much for that introduction. I think you've outlined really very well some of the main themes here, and I guess my main takeaways from that are that it's a combination of two things that are going to make this technology or allow the technology to develop to be fit for purpose, and that's firstly having an ambient pressure reactor, which in turn allows this smaller EPZ, which we've talked about, and secondly combining that with this ultra long fuel cycle, which means no refueling in ports. Now we're going to come back to the fuel cycle later on, because it's an absolutely fascinating area and it changes some of the fundamentals that we know about shipping absolutely upside down. But first, I'd now like to bring in another member of the team, and that's going to be Tom. Tom, I know you've been looking closely at the effects of mass manufacturing, and you have a number of slides to present as well. But if I can start by asking you, because this kind of naturally follows on from William's talk, is that we've heard about moving to assembly line production there, and we've touched on it several times over the course of these virtual programs as well. Now, of course, Core Power is just one of many companies involved in the development of advanced reactors that's looking to make this transition from project to product. I wondered, what's your take on why it hasn't been done before? Is it just as simple as that it comes down to the size of the machines at the end of the day, or is there sort of more at play than that?
Yeah, thanks, Toby. I mean, this is an interesting question. So the proposed leap, as you mentioned, from project to product has come about in direct response to the increasingly high upfront costs of nuclear. And it's been this transition that is something that's already received significant support and consideration from the industry. However, this transition has only been made possible with the more recent advent of small modular reactors, or SMRs, which has meant that now nuclear reactors can be of a size which can benefit from both modular and factory-like construction. And now, while there's clearly great potential for change here, there's also been hesitancy. And this is because there is now no clear path on how logistically we can so drastically change the construction process of a nuclear power plant. And this has also begun to raise questions on what sort of form this construction facility would take. Now, this is where we believe modular shipyard construction can play a potentially game-changing role for the nuclear industry. So first, I think it's important to understand what has caused these inflated upfront costs. Now, primarily, this has been because conventional nuclear power plants have been large-scale, complex, one-off projects. And this has effectively meant that each of these projects has always assumed a first of a kind, with a limited design refinement and a repeatedly changing workforce between the projects. As a result, cost and time overruns during construction have now become common, which has created uncertainty around the inflated capital requirements for this technology. Now, this has often resulted in nuclear often being undervalued as an energy source, and this is despite its clear operational benefits, such as a high capacity factor and its much lower operational costs. Now, when attempting to reduce these costs as we are, it is important to understand how they are broken down. Now, despite common misconception, most of these costs are actually associated with the nuclear island and turbine equipment. As we can see here, they only account for around 20% of the total cost. The other 80% includes construction, installation, labour work, cooling, and financing. And now it's also important to note here that for the financing costs, this includes interest changes in debt, which is something that is increasingly important for the longer construction period time that is associated with nuclear. And now it is in this 80% of the costs where we see there is a clear opportunity to reduce the capex issue that has so far held back nuclear deployment. These costs have actually already caused significant variations in the global construction cost of nuclear, and this can be seen quite clearly on the graph to the right here. Now, this graph shows the projected cost range of a number of proposed and operational nuclear deployments. Now, clearly these inefficiency premiums have had a considerable impact on the total asset cost, with some of these in the range of 3 times different. Now, typical causes for this has included reduced labour productivity and delays caused by changes in both the workforce and the particular local conditions at each of these construction sites. Now, a recent study conducted on US power plants actually found that labour productivity had fallen by up to 13 times lower than the industry expectations. Now, it is these indirect costs which have historically not actually been prioritised, with research now indicating they are able to cause up to a 70% increase in the original cost. I think this is pretty evident from the graph here. This can often directly correlate to the loss of the economic justification of the project, and it's also critical for pricing of electricity, which is often based on the cost of the asset. However, it is also important to note that this variance also clearly indicates that substantially lower costs are achievable for nuclear. Now, here is where we believe shipyard construction offers a game-changing opportunity. This industry, in stark contrast, has thrived on large-scale fabrication of complex assets, and it has done this by using a skilled, consistent workforce to achieve low cost, high productivity, and high-quality construction. As a result, the shipbuilding industry has been one of the first industries with a verifiable learning effects, and it has seen substantial improvements in productivity in the same time that the nuclear industry has struggled. Now, one way that shipyards have been able to achieve this is by utilising modular construction, which has allowed the transition to factory fabrication. Now, in this way, each module is manufactured in controlled factory conditions, and it eliminates the need for any site-specific work, offering an integrated manufacturing, assembly, and installation process all in one. In this way, several processes can be conducted in parallel, reducing time overlaps and increasing construction efficiencies. It is also important to note that the shipyards can provide efficient decommissioning sites for floating nuclear assets, a process that has often caused difficulty for nuclear in the past. Now, as mentioned, this transition is a key strategy that nuclear hopes to adopt following the advent of small modular reactors. Now, Core Power is working towards this transition and proposes utilising shipyard construction, which has already had such demonstrated success in this area, as this would offer a plausible route to make this transition. So the integration of this manufacturing strategy has actually already been proven successful in the nuclear defense industry. So in order to maintain affordability, the Virginia-class program for US Navy attack submarines had to aggressively reduce its costs and schedules. So in response to this, a small modular reactor was developed for use while construction was moved away from a temporary facility to a dedicated factory, which closely mimics what the environment that Core Power is proposing. As a result, the build time for the first of a kind was reduced by 29% per submarine, and the cost per hull was reduced by 17%. It's also important to note here that the increased learning effects associated with modular construction will result in further unit cost reductions as there is a transition from first to nth of a kind. In fact, the latest ship produced by this project was actually delivered 8 months ahead of schedule and a further $90 million under budget. Clearly then, there has already been proven success of this strategy for the nuclear industry. Now, as we look to the future of nuclear power plant construction, I want to specifically discuss 3 of the key benefits that will apply when this construction is moved to a shipyard. Now, the first is the speed of construction. So unlike a stick and built site, where it must first be properly outfitted before construction can start, a shipyard is already outfitted perfectly for use. And this offers a skilled workforce and a factory environment. In this way, productivity for nuclear construction can be brought in line with shipyard construction and avoid the extensive delays that have become common for terrestrial plants, improving both the uptime of the asset and the shipyard. Now, there will also be a decoupling between plant construction and site licensing, with no need for site evaluation and preparation. Therefore, these processes, similar to those on the factory floor, can commence independently, further reduce the deployment time. As a result, we foresee a 36-month construction period for the MSR floating power plant, which is 3 times shorter than the current industry standard, increasing the speed of commercial deployment while benefiting from an increased learning rate as the number of units increases. This increased deployment will also allow the design to be further refined and finalized after each unit, allowing the transfer to greater parallelization and further reducing construction time. Now, obviously, the increased speed of deployment will in turn have direct impacts on the price of the asset. So unlike terrestrial plants, modular shipyard construction will increase the speed of delivery while assuring costs. This in turn will reduce the interest and lower discount rates on capital investment, lowering the financial risks of this technology and fostering wider commercial investment and deployment. Now, shipyard construction can also reduce the required materials while also reducing waste. For example, a shipyard constructed floating nuclear power plant will also be made mostly of steel with virtually no need for structural concrete, which has contributed to significant delays and cost overruns in the past. Now, by transitioning to shipyard construction, there will be a reduction in the required concrete by up to 30 times, providing a substantial reduction in the required resources and successfully reducing costs. Now, in this way, a shipyard constructed floating nuclear power plant will be able to provide the economic advantages of factory production while reducing construction costs by eliminating excavation work, resource requirements, temporary facilities, and the associated labour. Now, in turn, this will close the gap between realised and expected costs and bypass one of the greatest current barriers to wider nuclear deployment. Now, while sometimes not considered cost saving, safety during construction process can also be a big cause of indirect costs. During construction, the factory environment of a shipyard can enable safety requirements to be easily monitored and designed into each module, while using a consistent and skilled workforce to repeatedly complete the same task. As a result, accidents during construction can be reduced by up to 80% when a modular construction method is used. Simultaneously, the increased monitoring and training will also ensure that quality assurance is designed into every step, resulting in an improved quality control procedure. So to quickly summarize, the current nuclear industry has been hampered by cost and time overruns, and it has often resulted in massively inflated capex requirements. Now, by contrast, the shipbuilding industry has thrived on the large-scale fabrication of complex assets in a controlled factory environment while utilizing modular construction. Therefore, we believe combining these 2 industries is a potential game changer for the nuclear industry, offering a skilled workforce and a site that is already fitted exactly for purpose, with no chance of disruption from local conditions. It can also offer a plausible route to modularization while benefiting from the associated shipyard construction advantages, such as faster deployment, cheaper manufacturing, and higher levels of intrinsic safety, overcoming many of the most capital-intensive processes in current terrestrial deployment. Now, we believe this can help marine nuclear to achieve its economic goals while benefiting from faster, more repeatable construction, bypassing one of the most significant barriers to widespread commercial deployment. And with that, I will hand back to you, Toby.
Well, many thanks, Tom. Some very interesting points you make there, particularly around the non-technology costs, actually. And I was surprised to learn that could be as high as sort of 80% for a terrestrial gigawatt scale plant. Obviously, that's clearly significant, and some huge savings can potentially then be unlocked then by this creation of a central manufacturing hub. Now, be that, it could either be a nuclear shipyard or a plant that is co-located with a shipyard. I mean, even if the resulting asset then has to be either wet towed or put on a heavy lift vessel for its mobilization voyage, that additional cost I think would probably pale into insignificance when you don't have to contend with all those challenges of building on site that you outlined. So thanks very much again. Now, our final short talk today is from Mikhail. This will look in a bit more detail at the topic of residual value of energy. And there's a fascinating and very fundamental difference here, not only between new nuclear and fossil fuels, but in fact also even between new nuclear and conventional nuclear, which we need to properly explain. And Mikhail's going to do just that for us today. William sort of mentioned it in the introduction. The magic elements of this are in the liquid fuel salts and the inline refueling, but the floor is yours, Mikhail, so I'll let you go into more depth on this, because I think it's not an exaggeration to say that this is really perhaps the most game-changing part of the whole new nuclear offering.
Thanks, Toby. And thanks to Tom and Will as well for really interesting views into how this is likely to work. As you said, Toby, I'm going to talk about the economic principles around the idea that we change the way the fuel cycle works. This idea that we can keep the fuel going for an awful lot longer than what is conventionally the case in nuclear today. So I've called this disruptive economics of new nuclear for maritime, and that really talk about some of these economic concepts and the high residual value of the energy that Will was alluding to before. The way that we do this, let me just make sure this works. There we go. I'm going to describe the way that the conventional nuclear fuel cycle works today. So it will explain that when we think of nuclear, we think, especially for maritime, we think of naval reactors. When we think of nuclear in general, we think of large power stations. And they, 99% of all these power stations run on this conventional fuel cycle. And the conventional fuel cycle is the one that requires frequent refueling and produces nuclear waste that has become a contentious issue in the public domain, etc. And the reason for that is quite simple. The conventional nuclear fuel cycle has the nuclear fuel and the coolant of that nuclear fuel. The coolant is the medium that cools the reactor and also transports the heat from the reactor core out to the power conversion system that creates steam or electricity from that steam. So you have the separation of the fuel and the coolant. And that's important because it means that you can take the fuel out and you can replace it with new fuel. So what happens in one of these is that, in the conventional nuclear fuel cycle, is that we have a fairly frequent refueling. We are using very low enriched fuels. And of course, the frequency of refueling is related to how enriched the fuel is. So in conventional nuclear power plants, you're running up to about 5% enrichment. So that means that 95% of the uranium is natural uranium, and 5% of it is enriched so that it can cause a chain reaction in the reactor and create the heat that we want. Now that means that within a couple of years, maybe slightly longer, we run out of the energy in this fuel. It starts to falter, and we have to stop the reactor. It means that we have to stop for refueling. And when we refuel a reactor, it's not like we're just topping up because there's no fuel left in there. All of the fuel is still in there. We're just not getting energy out of it. So we're now removing all of that fuel, or most of that fuel, by opening the reactor, taking that out, and then putting fresh fuel back in again. So there's a nuclear fuel, sort of fresh fuel supply chain required on the inbound to these reactors. And then, of course, you've got that difficult issue of removing the fuel and what to do with the fuel afterwards. Now, the question of what to do with the fuel afterwards, of course, comes down to, do we reprocess this fuel or don't we? If we do reprocess the fuel, then some of that fuel can go back into the fuel cycle whilst storing the resulting nuclear waste, which, there is, of course, a lot less of. If we don't, then all of it goes to nuclear waste. So typically in America, in the United States, they do not reprocess the fuel. So all of the spent nuclear fuel goes into storage. In Europe, France, UK, many other places, Russia, Japan, etc., fuel is reprocessed so that some of that fuel goes back in. So some of that fuel then goes back in the fuel cycle, and on it goes. So this is a fairly costly and involved process, which of course is one of the also reasons why the operating expenses of nuclear is quite high. So if we look then at the economic principles of this conventional fuel cycle, most of it is focused on operating expenses. The capex, as Tom has spoken about, is high, and there are good reasons or specific reasons for that. But in addition to that, we have this operating expense. And these are broken down generally into the following areas. So we've got this cost of specific designed fuel pellets. Each one of these reactor designs will need a specific size and configuration of the fuel pellets that go into the fuel assemblies. And there's millions of these pellets in each one of these reactors. Then we need these solid fuel assemblies. These you may have seen pictures of these. These sort of large tubes made out of zirconium that are then geometrically arranged in such a way that they can be lowered into a nuclear reactor and then function properly and taken back out again. And then, of course, when we stop for refueling, we've got the power outage. It can take anything between a month and 3 months to refuel a conventional reactor. Some do it faster, but actually sometimes it takes even longer. So of course you've got the power outage during that time. You're not producing revenue from power production. Then we've got the cost of the fresh fuel supply chain. Now, uranium is still quite cheap, but you've got the enrichment process, you've got the transport, and you've got that process of refueling. And then of course now we've got to take the unused fuel out. It's not nuclear waste, so to speak. It's just unused fuel, the energy that we haven't used yet, and we have to then take it out and we have to store it either intermittently because it's going into reprocessing, or for the longer term because we're not going to reprocess it. And then of course you've got that cost of long-term storage, security around that's required, and then at the end of the life of this thing we need to decommission, and that's of course something that's expensive. If we reprocess the fuel, we've then got to add the cost of nuclear fuel transport, which is from the reactor site to the reprocessing site. That can be on the other side of the world. It can be from, for example, from Japan all the way back to the UK for reprocessing, and then that fresh fuel goes back again. The reprocessing costs are not trivial at all. And then, of course, once it's reprocessed, the nuclear fuel has to be transported back to the reactor site. The waste that's left over, that little bit of footprint that's left over once the reprocessing period is over or process is over, the long-term storage and security of that, which is fairly long-lived nuclear waste, also has to be encountered or counted for this. So it's really an operating expenses added to the capital expenditure of building nuclear plants that have to be considered very carefully. If we then look at the new nuclear fuel cycle, this fuel cycle that we're describing here, that William was alluding to with the fast molten salt reactor, the basic principle is that we are trying to achieve what is being done in naval reactors, is where you have where they operate an extremely highly enriched fuel, which does not need to come out of the reactor. You do not need to refuel it, but it's something we cannot do. So we need to operate with a low enriched fuel, and we must maintain that benefit of having a long fuel cycle for the reactor, which means that we need to create a situation where the energy inventory of the reactor is always full. The nice thing about this molten salt reactor concept is that we combine the fuel and the coolant. So we don't have a separate fuel from the coolant. So in a sense, we cannot remove the fuel from the fuel salt. It is already combined in it. So we have a much simpler way of operating, which is quite good. The way that we intend to maintain a full inventory of energy at all time is to do continuous inline refueling. You can think of it like conceptually like a hamster drip. dripping fuel into the reactor on a frequent basis. Of course, it's not going to function like that, but that's the concept. So you're topping up that little bit of fuel that you're using. Remember the fuel efficiency here, as Will again said, you've got 80 million megajoules per kilo per ton of fuel here, and you have very, very slow usage of that. So we're topping up with very small amounts of fuel. And then at the back end of the reactor, we have a cleaning system so that the fuel, as it passes through around the reactor, is then cleaned. So we have a fuel cleaning system that takes out noble gases, takes out some of the impurities, some of the fission products, etc., and then stores them securely in the reactor island, again, so that they're not extracted, they're not released into the environment, they're not available for anybody to move around. They just stay with the machine. Now, by doing this, we can continuously maintain that full energy inventory in the reactor and emulate the benefits of having a very long fuel cycle. Of course, that fuel cleaning becomes nuclear waste, but again, it's just the energy that's being used, not the 99% of the fuel that is consistently not being used. And since it's small, we can store it efficiently and not release it into the environment. The economic principles of this new nuclear fuel cycle combines the capital expenditure and the OpEx and the operating expenditure. So really the main cost elements that we're looking at here, which is, of course, not related to building of the reactor and the reactor system itself, but to the fuel cycle, is the cost of correctly enriched uranium oxide. So we're now no longer talking about having pellets, configured, specific, designed pellets that go in. This is made just purely an oxide. It's a powder form which is correctly enriched for that particular reactor system. Then we have the cost of the inline refueling system, which is not trivial because you can't just pour fuel in by eyesight. You have to do this, scientifically to make sure that the correct amount of energy is in the reactor. And then, of course, we need to monitor what that fuel inventory is. So there's a cycle there of monitoring, topping up, monitoring, topping up, etc. So that fuel inventory monitoring system, which in a very hot environment, of course, is going to be a robust and it should be fairly simple to operate, but should be reliable as well. Then at the back end, of course, we need that fuel cleaning system. And again, this is not a trivial thing. I mean, these are complex chemical compounds, etc. Some of them are statistically unknown, and they must be either kept in the reactor, or if they're coming out through the fuel cleaning system, need to be dealt with. So this is it should be a fairly simple system that identifies what needs to be brought out, or we identify what needs to be brought out, and the fuel cleaning system then takes that and cleans the fuel of those impurities, so that we don't build up impurities in the fuel and then cause degradation of the machinery, or even shorten the fuel cycle for this. And of course, then eventually that fuel residue has to be removed. So at one stage, maybe during periodic maintenance, that those casks or those boxes with that nuclear waste in it needs to be taken out and put into storage. And because they are fairly lively, we're talking about short to medium term storage. There's no long-term storage of nuclear waste in these reactors, because all that long-term actinides that are caused by the chain reaction are in fact consumed inside the reactor. So it shortens the life of the waste, and of course it reduces the amount of waste that we do. Then of course we got eventual disposal and recycling. At the end of the cycle, so that's the end of the cycle of the reactor, not necessarily of this inventory, we need to decommission those machines. So that's a cost that comes, just like with any other machine, that needs to be scrapped or decommissioned. And then of course we need removal and cleaning of that fuel inventory before we can load it into the next generation of reactors. The idea is that since the energy is always intact and the fuel should be clean enough to be continued to be used in other reactors, we can keep loading it into next generation reactors again and again and again, rather than continuously replacing all the fuel. So the way that we think about this is really to try to create sustainability, not just in the inventory, but sustainability in the energy supply to marine assets. And of course, if we can use this on land or for other purposes in the same way. So here you have the same concept then brought across several generations, again, using a 30-year time period where we're adding fresh fuel, cleaning it, taking out the waste, maintaining that inventory, the energy inventory always full, and then after 30 years, draining that fuel, putting into a second generation or next generation of reactors and doing the same process again and again and again. So essentially, you're reducing the amount of mining that's being done for fresh fuels, you're reducing the enrichment, you're taking away the need for reprocessing, and you're producing a much smaller quantity of nuclear waste, which is much shorter lived, which can be stored underground or in specific locations without too much difficulty. So again, a sustainable nuclear fuel inventory is really what we're looking for here. The capex up front then becomes a big number, but with the higher residual value, it changes. So if we're looking at the machinery, we're looking at the reactors and the asset. In this case, of course, we're looking at a vessel, but it's just for example. These are principles, not exact examples. We're looking at the asset depreciation of the vessel. We've priced it as a 60 million ton Newcastle-Max bulk carrier, and we priced her at 100 million, just assuming that she's going to be more expensive because she's a nuclear powered ship. The asset depreciation is down then in straight line depreciation over 30 years to say 10% of its original value. So she goes from 100 million to 10 million over 30 years. So that's $90 million in straight line depreciation. Not taking into account, fluctuations in markets and loan covenants, etc. The reactor depreciation, we're adding to that the cost of decommissioning. So this decommissioning fund, which is basically a number of dollars per megawatt hour produced, which is then added to that depreciation and added to the cost of operating this, so that at the end. But what we've done very conservatively here, Toby, is we've said, okay, this is going to zero. We're not going to have any scrap value in the metal or in the machinery, etc. Of course, there is that possibility that we could reuse this if they have longer periods of time. So that's the machinery side. Now, if we're looking at the effect of inflation, as Will again pointed out, at 2.5%, inflation will cause the doubling of value of an asset, all else being equal. A well-maintained asset over 30 years, 2.5% inflation will double in value. Of course, now we've got inflation at 10% in the UK. We have slightly less other places, slightly more other places again. But a long-term inflation of 2.5%, I think, is sensible. So we're looking at the potential increase in the value of that fuel inventory as it goes along. Now, naturally, OPEX would increase by inflation, and as would the price of everything else. So this is a principle that sits at the heart of the way that we would think about financing this. Now, if we then look at the effect of all of this, and this is the same chart that Will showed earlier, but it's really about how we could create a leasing model around this. And I'll talk a little bit afterwards about why we would create the leasing model. But a leasing model is an interesting one because we've got this potential lease spread, that the potential for a financing, from a finance perspective, to depreciate the fuel. Here we've gone from $250 million to $200 million. We're depreciating the value of the energy by $50 million over 30 years. And if you add that to the $10 million scrap value of the vessel, you've got $60 million in depreciated value. So you're going from 500 million capex to 60 million in a residual value of the entire island, if you like. Now, that's a fairly burdensome financing task for those who would operate these vessels, and would probably make them quite expensive. But if the actual value of the fuel comes up from 250 up to $500 million or anywhere near that, of course, we can change that. We can change that residual value. We can move that $250 million up to flat, so it's still 250. We can move it up to 300, 350. We can move it all the way up to 500. But in between there sits that potential for a lease margin where we can have the cost of capital, the cost of operating the systems, of course, the profit margin for the manufacturers and the operators and everybody else can be built into that. What is effectively, in this example, a $300 million lease spread over time here. So you're looking at something which is 60% of the total capex, which still sits there in additional residual value. So we think there's real potential here for creating a very interesting leasing model. Now, why would we create a leasing model on this? Now, a couple of things that we have to remember. We need, at all times, and these are the rules, so we don't make these up. These are the laws as they are. Ownership and inventory control of nuclear fuel is tightly regulated. We cannot have anybody going out and buying nuclear fuel and operating nuclear fuel. You have to be licensed to do so. Of course, they're also export control related. You cannot just buy enriched fuels from anywhere and move it around. There's very close export control list, so they have to be done in jurisdictions within certain flag states and in certain areas. So you can't just freely move them around, not yet anyway. The second thing is there is no second-hand market for nuclear fuel. Once you've got spent nuclear fuel or nuclear fuel that can be used again, you can't just put it on the market and see if somebody else wants it. So it has to stay in the cycle, if you like. And then the responsibilities of the operating this, of course, of the machine sits with the design holder. That's the designer, the manufacturer, the vendor of the machines, and of the operation of that reactor, whether it's whatever type of reactor it is, and of course the responsibility to the fuel sits with the duty and the license holder. The duty holder and the license holder is the licensed operator of the reactor. Then at the end of it, of course, we need the nuclear waste and decommissioning that needs to be managed, and that again ties back to the duty and license holder. It's the responsibility of that person. We do not see how, at least not in our lifetime, how the majority of commercial vessel operators, ship owners, and offshore operators, etc., will want to or could even become licensed nuclear operators. We think this is something that has to be combined with those that are already licensed to do so, and being able to if you like, create a leasing scheme where the power and the machinery and the use of that system is a lease to the operators. And of course that has some clear advantages as well. Stable cost of energy. A lease plan is, same payment every month, same if you lease a television or if you lease a car or anything else. And then you have that opportunity of using that stable cost, that fixed cost, versus that floating price that you can charge for using that vessel, in the charter markets, whether it's container ship or dry cargo vessel or a tanker or a floating assets producing power. You've got a floating price for that, which gives opportunity for trading and profit margin, but it sets a fixed low cost, which is very important. We think all of this pretty much adds up to what is an exceptionally powerful, disruptive economic model on how marine energy can be both produced and used. So with that, Toby, I'm going to hand that back over to you and then see if we can get a panel discussion going.
Great, thank you very much, Mikael, for that. It's always interesting for me to learn a bit more about the this topic of the fuel salt life cycle, and you obviously also managed to tie that in today with how that lease spread might look on the fuel inventory, and see 60% of the original capex really is quite a significant number, isn't it? So now we've heard from all of our panelists today individually. I'd like to open up the discussion to include all of them together. We've examined the economic benefits from a few different angles, and we've looked a bit at this concept of shipyard construction. I wondered, would the panel be able to sort of expand on that a little, as it seems as though the main benefits will be derived really from the perspective of a floating nuclear power plant rather than another asset. Is that really the case?
Julia, do you want to answer that? Julia, you're muted.
There are a lot of efficiency that can be derived from shipyard manufacturing, as Thomas has very well demonstrated in his slides and with his arguments. And another very important, I think, efficiency is related to the decommissioning, and which has not been discussed here, but it's extremely relevant. Nowadays, nuclear plants are decommissioned at site. So the site initially becomes a construction facility, and at the end of the life of the plant, it becomes a decommissioning facility, with all the cost of outfitting every single time each different site. With a floating power plant that can be decommissioned in a centralized facility, these costs are borne once for all. The site can be very well outfitted to do things efficiently, quickly, and safely. And also we should recall the remark about safety, work safety, and injuries in general for construction at site while safety on an industrial facility. So these are extremely important matters. Now, also in this respect, when we run technical economical evaluation and we consider, let's say, the cost of treating and storing the waste and the cost for decommissioning, we basically use the same value for the current nuclear land-based industry, and these costs are about 3 cents of a dollar per kilowatt hour. In a conservative way, we are using basically the same cost, while this reasoning shows that this cost could be much lower, so bringing further economic benefit also on the decommissioning side.
Thanks, Giulio. I'm glad you clarified some of those parts, because I think a lot of people still assume that nuclear vessels may in the future somehow end up on a beach in Bangladesh with their reactors exposed for anyone to pick over, and clearly that's not the way this has to work. I think the ship recycling sector has its own ESG hurdles to overcome, and we obviously don't know what that sector will look like in 30, 40 years' time by the time a first generation of nuclear ships are decommissioned. But there are clearly
Toby, if I may, so now we know that the Hong Kong Convention has not already completely, let's say, ratified and is not enforced, but with a nuclear vessel, I mean, something like the Hong Kong Convention, you need to have there from the beginning. So the compliance with the decommissioning of the vessel is not something that will be considered at the end of the life of the vessel, but will be part of the design of the operation of the vessel as a whole. So also from the environmental perspective, there are much more safety and safeguards than there are actually currently are for conventional ships.
Absolutely. No, thanks for clarifying that as well. I'm going to take a few questions that have come in now, and there's one here for you, Mikhail. We've noticed that the ship in your slides retains its small residual value as you'd expect it to, but that the reactor is actually depreciated to zero. Is that sort of in line with the expected lifespan of the reactor? How does that relate to the design life? Is it potentially overly conservative?
I think it is very conservative, Toby. We just don't know yet. You know, new generation of technologies like this that's designed for a 50-year lifespan, you know, and used, you know, in these environments, could have a longer life, could have a shorter life. We don't quite know yet. So at this point, I think the only sensible thing and the only responsible thing to do is to say, if we're designing for a 50-year life or a 40-year life, let's assume that we can get, you know, absolute high quality life out of that for 30 years. Let's finance it for 30 years and let's write it to zero, including decommissioning at the end of 30 years. Anything else really then comes as a bonus. I think if we can, you know, if we can reuse it for 25 years, it seems perfectly reasonable that it would continue for 50 years, then we will simply keep on using it or shift it from one asset to the other. I think that's the sensible thing to do. Of course, you know, whether the you know, a reactor that was designed 25 years ago is really fit for purpose in, you know, an asset that may be built 25 years from now, it's one that we can't answer. I think there's a lot of changes going on in this industry. There's a lot of disruption in all manner of different ways. So it could well be that we just need to stay conservative at this stage and not overpromise, rather over-deliver, I think.
Understood. We're going to shift topic slightly back to this concept of shipyard construction. Now, this one is coming for you, Tom. How do you envisage MSR construction to be integrated into existing shipyard functions? Do you have any comments to make on that?
Yeah, no, so this is obviously something that will be important to consider in the future, and we're not naive to the fact that obviously nuclear construction will involve, you know, very specific processes and technologies that, you know, aren't currently found in a shipyard. But this is something that we've begun investigating, and we believe that generally it will be based on sort of existing shipyard practices, with the MSR element forming its own module, sort of similar to that modular construction that we discussed earlier. And now, while the introduction of the required modifications to the shipyard will be, you know, an issue, it will not be as insurmountable as it might seem. Now, because in today's markets, shipyards have had to continuously invest in improvements to their systems, and this is to remain economically competitive. And we believe this will likely fall into sort of the scope of this.
Absolutely. Thank you for that. That's great. A question has come in on an aspect of the commercials that we haven't touched on too much today, and that's actually during operation. How does the option for higher speeds for nuclear-powered vessels impact the economics? Julie, I know that's something that you've looked at a little bit when it comes to container shipping. Are you able to comment a little bit there?
Sure, Toby, thank you. Well, as we all know, ships need to be operated close to the economic speed. That means the speed that maximizes the profit. And of course, with ships running on fossil fuel, either due to the high cost of fossil fuel plus carbon taxation, the economic speed will reduce in the years to come. And at the same time, if we look at the green electrofuels, the high cost of this fuel will also have a big impact on the economic speed. On the contrary, for a nuclear power vessel, due to the lower life cycle cost, we will actually have a higher economic speed, or at least a non-lower economic speed in respect to the other vessels. So this will mean that with the same, let's say, ship capacity, you will have a larger throughput, a larger amount of goods transported over time, instead of a reducing amount of goods transported over time. In addition, due to the fact that the operation of the speed the operational speed has not an influence on the OPEX for nuclear ships, but on the CAPEX. Once you have designed the vessel for a particular speed, you will try to operate that vessel as fast as possible to maximize on the return of the CAPEX. So it will bring quite a change. We think that for container ships, for sure, it makes a lot of sense to go back to pre-2008 design and operating speed in the range of, let's say, 25 knots, but even higher speed are achievable. For large, let's say, bulkers and tankers, those are, let's say, mass carrying ships rather than volume carrying ships. These are ships with a very high block coefficient. So some increase in speed is feasible, but not a large increase in speed. Otherwise, let's say the resistance, the ship resistance in water increases exponentially, and it becomes economically infeasible.
Excellent. Thank you, Giulio, for that. I think we'll take one last question from the pool of questions that have come in before we wrap up. I'll open this to throw this out to the panel in general and see who'd like to pick up on it. What is your current target for this technology to be available and accepted for use on commercial ships? And are you targeting also the retrofitting markets as well as the new building market? Interesting question, that last part, which we do get asked quite often.
I don't know. Any thoughts? I'll do the first bit, and then I think I'll pass over to the rest of the panel. Timing is an interesting one as part of this. I think if we're looking at this in a straight line basis from where we are today to where we think or where we see the potential for the first deployment, we're looking at somewhere in the early 30s, but that's on a demonstration basis. It's potentially possible to do that faster. It relies on a number of things. I don't think it's necessarily technological. I think it's regulatory, licensing wise, and financially. To get that done faster, it just needs an orders of magnitude higher intensity in the development program for this. So that really, I think, depends then on, who are we building this for first? Are we building this as a prototype for a general market, or are we building this as a prototype for a specific customer or specific type of customer, and even in a specific place? So I think the regulatory, the licensing, the financing, and the sort of the operational envelope around this all depends very much on that last question. And of course, under the surface, there's a huge amount of stuff going on that we can't reveal, but I would say, all else being equal, early 30s.
Thanks, Mikhail. That's very helpful. And then the second part of that question related to the concept of retrofitting versus a bespoke new build. Giulio, that's maybe one for you, but anyone else feel free to jump in.
Sure, Toby. Yes, I was considering that question. So from the technical perspective, it's perfectly feasible to retrofit a reactor on an existing vessel. I mean, we all know that ships are cut, lengthened, and modified In the past, a container ship has also been, let's say, widened. That was a great engineering task. The thing is that when we consider the cost of the nuclear ship as a whole and the cost of the reactor, we see that the cost of the hull is marginal. So, in my opinion, there is hardly an economic case in taking an existing conventional ship, which relatively residually low value, and make it a new a nuclear ship out of it, rather than building a completely new ship. That would make much more economic sense. So it is feasible from the technical point of view, but economically, I think it doesn't stand very much.
Sure. Thanks, Giulio, for that. We've had some last minute questions come in on the subject of Japan, on the subject of the smaller EPZ, and on the subject of sort of the whole concept of nuclear shipyards. But I think in the interest of time, because we've gone actually just slightly over the hour, I will try and take those questions offline and get back to you all individually, if that's okay. So I just want to thank the panel very much for your contributions today. To close today's program, I'd like to just give you a quick flavor of what the next month or so looks like from our perspective. This time next week, we'll be presenting again on this topic at the 14th London Ship Finance Forum, hosted by Marine Money. The talk that we're doing is very much linked to today's subject matter, as we outline new nuclear as both the economic and environmental disruptor. We expect there'll be some excerpts available from that event, so please keep an eye on our website and our newsletter if you've not signed up for that yet, and our social media channels for more details. In terms of other events that we're running related to our client program, the Singapore conference is very close now. It's 3 weeks today exactly, on the 9th of February. And if you are in the Asia Pacific region and have an interest in maritime nuclear, I would really urge you to book up your place at this event now. It's the first full conference to take place in the region. We've got a lot to discuss, not just about some of the economics that we've looked at today, but I think we have a total of 16 sessions from start to finish throughout the day, covering the wider topic from all angles before moving into a social networking event in the evening. There's a link to the event from our homepage where you can register, or just let us know if you'd like a place and we can do the rest. Looking further ahead, we're also now confirmed as a significant sponsor of London International Shipping Week, which is in September 2023. So we'll be anchoring that program with an event on the 12th of September. Again, please keep an eye out for details, and it will be great to meet some of you in person at one or more of these larger events. But for now, all that remains for me to say on behalf of our panel is we hope you've enjoyed today's program. We very much appreciate you taking time out of your day to join us. Have a good rest of the week. Thank you very much, and goodbye.